Okay, so now in this example, we see the photon is leaving. Okay, so the photon is exiting. So if the energy level was, or the electron was in this energy level and a photon left, now it's at a lower energy level. Okay, so anytime that we have a photon leaving, we know that electron moves down. We can therefore conclude that the photon was emitted, which means that I need to use my bright line or emission spectrum. Okay. For developed energy level diagrams to help explain his model of the atom. The energy levels in Bohr's model are not equally spaced, and it will vary for each element. They're not equally spaced because it's kind of to scale of how much energy each has. Okay, so here, let's look at some of this terminology. Here it says ground state. So that's like, it doesn't have, this is the closest to the nucleus, okay? So ground state means closest to nucleus. And electron is unexcited. Okay? So we label this as n equals 1, and these n's stand for energy levels for electrons to occupy. Okay. So now, hi.
How does the excited gas make the photon leave?
How does an excited gas make the photon leave?
Shouldn't they technically still be going to nothing?
So like in which example? The
When he used the excited gas and it emitted the photon?
which one? Here. Ah, right. So it's like it's releasing energy. It's releasing energy in the terms of photons, which are shown in the emission spectrum.
So this photon's emitting back to me already?
It's that, okay, it's that there's electrons that since they behave with a wave particle theory, that if the electrons move, they will either release or absorb energy. The energy is in the form of a photon, okay? So a photon is like the light. So with the gas that made the emission spectrum, the electrons went down, okay? The electrons went down a level and emitted light. So when you think of like light emitting, it's like it released that light, and the light is in form of a photon. Well, light is photon. But it's like, think about your muscles. Your muscles are just muscle, but they have energy. When you move them, energy is released in the form of heat, right? It's like an electron is an electron, but when it moves, it releases photons. Okay? So yeah, think about electron movement releases photons just like your muscles release heat when they move.
I don't get how an electron can go from excited to unexcited.
If energy is added to it or if it's not. So at ground state, it's like it's like a completely neutral atom. There's nothing happening. Yeah. And so if we look at the next term up here, ionization. Okay, so when we think about an atom, say like, I don't know, aluminum. Well, we know aluminum can become an ion and be Al3+. But how does it get there? Well, that aluminum atom has to gain energy, and the electrons will move up the energy levels, and if they move up high enough, that atom now becomes an ion. Yeah, it's kind of crazy, right? Because it's combining what we know about ions and explaining it at a subatomic level. So here, yeah, where we see the term ionization, the electrons have gained enough energy to leave the atom. Because when you think about, say, aluminum 3+, that means that it's lost 3 electrons, right? Because it's positive by 3. So that atom, that aluminum, say, atom, gained so much energy that 3 electrons went all the way up and got knocked off. Now, if that, say, aluminum ion went back to ground state, it would need to lose energy. So all these calculations that we're going to do next are based on using Bohr's model and the conservation of energy. Okay, really important. This is because since we're talking about energy being transferred all the time through photons, we need to apply the principle of conservation of energy, which is principle number 5. Okay, so if we're going to talk about energy being moved around, we need to apply our conservation ideas. So when we're doing this, we can say, okay, we're often going to look for change in energy, so delta E, and that's always equal to our E final minus E initial. Now, think about this logically. What should the delta E represent? Does it represent like the electron? Does it represent the photon? Well, delta E should represent the energy that the photon has either released or absorbed. So think about almost when you're doing these questions as the photon kind of being the vehicle for the energy. So when you think about change in energy, think about the photon giving it or taking it. The electron is kind of like on the receiving end of that. So now, if we think about this numerically, if we get a negative answer, kind of think about like redox stuff, okay? If we get a negative energy, okay, so if we get, if delta E is negative, then energy was released. Okay? Because if we think about the photon as being the vehicle for the energy, if it's negative, there's less energy that the photon had, so it's photon energy release. And then vice versa, if it is positive, energy was absorbed. Now, a note to you that in your workbook questions, it's not going to give you the answers as negative or positive. It will just give it to you as the number. But you can say, like, so say you get the answer -3 electron volts. You can still say, like, okay, that's 3 electron volts that was released. You know, okay? But your workbook will only give you the numbers, not the minus or negative.